Hello students. So in the last two lectures we have studied a very interesting problem of step potential where we have taken both the cases when the energy of the particle was less than the potential height and another case when the energy of the particle was greater than the barrier height. So let me recap once again for 2 minutes so that we can move forward. Okay, so in the last two lectures, we took step potential. I would just recapitulate the important result what we learned in the last two lectures. Step potential. Okay, we had the potential like this. The barrier height was V naught at x is equal to 0, and then the particle was approaching from the left. There can be two cases when the energy of the particle E, case 1, E greater than V naught. That is, the particle is like this. Then we calculated, I claimed that classically the particle will cross the barrier. Classically, the particle will cross the barrier because its energy is greater than the potential barrier. Okay, will always be transmitted. And then I made the claim that quantum mechanically there is a finite probability of being reflected and transmitted. There is a finite probability of the particle being reflected and transmitted. And this we saw by calculating what are known as reflection and the transmission coefficients. And we have done in detail that these reflection and transmission coefficients are defined with the help of probability currents. And I showed you that the probability current is conserved both in the region 1 and 2. So, transmission of being reflected and transmitted, transmitted. Okay. So, when E was greater than 0, we got my reflection coefficient R, which was defined as the probability current reflected in region 1 to the probability current incident. Okay, so if you remember, my J1 in one region was defined as JA minus JB, and in J2 it was defined as JC. Okay, JA was H cross. In region 1 my momenta was K1, and in region 2 my momenta was K2. Okay, so and the definition of J was, just to remind you all, H cross K upon M, imaginary part of psi star del psi by del x in whatever region we are taking. Okay, we can calculate the momentum. By using this definition, when I calculated the reflection coefficient would be JB upon JA. And in JB and JA are both the currents in region 1, so the momenta is same. So I got this as mod of B by A square, which came out to be, just to remind you, K2 K1 minus K2 upon K1 plus K2 square. And then the transmission coefficient I get Jc upon the current transmitted in region 2 upon current incident. And this came out to be C by A. And because the momenta in both the regions are different, I got K2 by K1 here, C by A mod square. Okay, and this T I got as 4 K1 K2 upon K1 plus K2 whole square. Also, I showed that my R plus T is equal to 1. All these things we have proved in the last two lectures. Okay, so these two coefficients, they show that R is finite and T is finite. So quantum mechanically, there is a finite probability of being reflected and transmitted when the energy of the particle is greater than V naught. And then in case 2, we calculated when energy of the particle was less than V naught. So classically, what will happen? What do we expect? When the energy of the particle is less than potential energy, then my kinetic energy would be negative. So classically, the particle would reflect. Okay, but quantum mechanically, I claimed quantum mechanically, I said that again there is a finite probability of being reflected, probability of being reflected and transmitted. And then again in this region, by using the probability currents, we calculated R and T. And to our surprise, what did we get in this region when the energy is less than V naught? That we got R is equal to 1, if you remember. And so if R is equal to 1, you can check T, it should be 0. This shows that there is no transmission. But I told you that in region 2, my wave function was decaying. I had some coefficient e to power minus alpha x. So when I calculate the probability, there is a finite probability of tunneling. Okay, but we got P is equal to 0. Now we'll try to take a case. In this case, my barrier was infinite. Yes, in the step potential, x is greater than 0, it is infinite. So the transmission is ideally 0. But still there is some finite probability. Okay. Now, what is the appropriate example we should take? Now, in the next example, I will take this barrier to be finite. And then we will try to see that what expression do we get for T. Okay. So let us see that. Then there will be a lot more nice physics to understand from that. So now, let us try to take another example. Quantum mechanical tunneling. Okay, why I'm calling this tunneling, it would be clear in some time. Okay, now I'm taking a barrier of finite width. Earlier this was a step potential, but now I'm taking finite width. Let me take this as V naught. Okay, and it has a lot of practical examples. V naught, and this is also called as rectangular barrier. Okay, and the width of the barrier is L. This is x is equal to 0, x is equal to L. So now Again, there would be two cases. When the energy of the particle is less than V naught and the energy of the particle is greater than V naught. Okay, energy of the particle when it is greater than V naught, then quantum mechanically again there will be a finite probability of being reflected and transmitted, which you can see by calculating R and T. Okay, that I would leave as an exercise for you all. Now, here I would be discussing another case which is much more interesting, E less than V naught. Now again, classically, what do I expect? A particle striking with energy E less than the potential width will be reflected back because it has negative kinetic energy. So classically, the particle will be reflected back. Okay, because due to negative kinetic energy. But quantum mechanically, I am claiming quantum mechanically there is a finite probability of penetrating through the barrier. Okay, this penetration through the barrier is called as quantum tunneling. That is why I am calling that the particle is tunneling through the barrier. Quantum tunneling. This is referred as like this. Okay, quantum tunneling. That okay. So now again I will, in order to solve this problem, I will divide my problem into three regions, region 1, 2 and 3, and then what should I do? I should write the Schrodinger equation, write its solution, apply the boundary conditions and try to find out the probability currents and the reflection and transmission ratios. Now you all know the recipe of the problem. Okay, next. So let us consider here, a barrier of width L and height V naught. Okay, and we know that when x is less than 0, v is equal to 0, and also when x is greater than L. And v is equal to v naught when x is 0 to L. Okay, now let us write the Schrodinger equation in all the three regions. Okay, so in region 1, d2 psi 1 upon dx square plus 2m upon h cross square e psi 1 is equal to 0. Because my potential is 0, so I can take this as 2me upon h cross square is equal to k1 square. This is when x is less than 0. Okay, great. Now for region 2, here again in region 2, here my solutions are oscillatory, but here in region 2 my energy is less than V naught. So I will pull the negative sign, I will get minus k2 square, and again my solution would be decaying. My wave function here, it is oscillatory, and again there is no potential, again here it is oscillatory. Okay, so what do I get here? d2 psi 2 upon dx square minus 2m upon h cross square v naught minus e psi 2 is equal to 0. Okay, this is 2m e upon h cross square, sorry, v naught minus e. Okay, this is equal to k2 square. This is from x 0 to L. Then again in psi 3, I get same as psi 1. Psi 3 upon dx square plus 2me upon h cross square psi 3 is equal to 0. Again my 2me upon h cross square is equal to k1 square, x is greater than L. Great. Now, writing the solutions of these three equations, I should put, this is my boundary condition, capital A, equations 1, 2, and 3. Now, from equation, writing the solutions of equation 1, 2, and 3, what do I get? Psi 1 is equal to a e to power I k1x plus b e to power minus I k1x. X is less than 0, k1 is 2me upon h cross square. Okay, then I get psi 2 is equal to c e to power minus k2x plus d e to power k2x. Okay, you can also take here positive, here negative, it does not matter when x is 0 to L. k2 is equal to 2m v naught minus e upon h cross square. Okay, psi 3, again it is oscillatory, yes, but in the region 3 there is no reflection. Okay, so we don't have the coefficient for e to power minus I k1x, so I get only e to power I k1x. There is no reflection. This is x is greater than L. K1 is again same to me upon h cross square. Now you all know that at the boundaries my wave function and their derivatives are continuous. Equation number is 4, 5 and 6. 4, 5 and 6. Now applying the boundary condition, here there is no reflection in region 3. Okay, so there is no term of minus ikx. Now the wave function and its derivatives are continuous across the boundary, that is x is equal to 0 and at x is equal to L. Also one more thing, in step potential I neglected this term. Why? Because here in region 2 in step potential at x tends to infinity this term was blowing, but here we have a finite width of the barrier, so I am keeping both the exponentially decaying term and exponentially growing term. Okay, now at x is equal to 0 psi 1 is equal to psi 2 and its derivatives are also continuous. At x is equal to 0 is equal to del of psi 2 by del x at x is equal to 0. At x is equal to L, psi 2 is equal to psi 3 and their derivatives are also equal, are continuous. Okay, now applying these four conditions we get four equations in A, B, C, D in the coefficients. Okay, what do I get? Using these boundary conditions, we get A plus B is equal to C plus D. Okay, then its derivative, this is I'm doing at x equal to 0. I k1a minus I k1b is equal to minus k2c plus k2d. Okay, by taking the derivatives. Now at x is equal to L, c e to power minus k2l plus d e to power k2l is equal to e to power I k1l. Okay, psi 2 is equal to psi 3 at x is equal to L. Then their derivatives minus k2 c e to power minus k2l plus k2 d e to power k2l. You can just check the derivative of the previous equation. I k1 e to power I k1l. That's all. The equation numbers are 7, 8, 9, 10. 7, 8, 9, 10. Now, I'm interested in what? I'm interested in the reflection and the transmission coefficients. Okay, and you all know that already what we have proved, that my transmission coefficient is given by the current J in the third region. So that will be JE upon JA, correct? In the first region, my current will be JA minus JB. Second region, my current will be JC minus JD. In the third region, my current will be JE. There is no reflection. And this will be K1 upon K1. In region third and first, momentas are same. So I will get E upon A mod square. Okay, the probability current in region 3, number of particles, we can also say number of particles per unit area per second. You can check the dimensions of J. Okay, that will be probability per unit area per second. This will be this, and this is equal to E by A mod square. Okay, and if you would like to calculate R, that would be JB upon JA. Again, JB and JA will have same momenta. I will get B by A mod square. Fine. Now I am interested in T. What is my transmission probability? Okay, you all know that when I took the step potential, T came out to be 0. Yes. Now, when you calculate these four equations, okay, this would be a little tedious. Okay, solving these equations, this I would leave as an exercise. Solving, just you have to simply find the, substitute the equations. I need E by A. Okay, so you can find from these, solving these equations. Exercise. Okay, I don't want to indulge in these mathematical steps, though they are very important. Okay, but I would like to emphasize here the physics from the final result. So from these four equations, I would get T as E by A star into E by A. Okay, it's mod square, that is complex, so I will take E by A complex conjugate into E by A. That comes out to be 16 upon V naught into E, 1 minus E upon V naught, E to the power minus to K2 L. Now, this is interesting. What is K2? K2 is K2 square 2m V0 minus E upon H cross square. This is my result for the transmission coefficient and it is finite. Yes, when T is finite, R will be finite. So one thing is clear that when the energy of the particle is less than the potential height, there is a finite probability of being transmitted and reflected. Okay, and what more information do I get here? That my T, the transmission probability for a particle to cross the barrier, it depends upon two important factors, V0 and L. Yes, and how do they depend? It clearly shows from this formula that when V0 increases, what will happen? When V0 is very large, then this term will be very small, I can neglect. Okay, I will get 16E by V0. When V0 is very, very large, it tends to infinity. For example, if I say, then my transmission T tends to 0. Yes, this is extreme limit I am taking. So as V0 increases, and which is obvious, increases, that is barrier height increases, T decreases. The probability of being transmitted decreases. Obviously, when the height of the barrier increases, then the transmission will be less. This is my first point. Second, how T depends upon the length of the barrier. This is also negative exponential. As L increases, as length increases, length of the barrier increases, again the transmission, that is barrier width decreases, sorry, width increases, again my T decreases. Again, this is very obvious. So there are two things here. This is my V0, two factors, and this is my L. As V0 increases, T decreases. As L increases, again T decreases. Okay? So in both the cases, T decreases. And now we can see the case of the step potential. And obviously, what do I expect from this result? In step potential, my length is, so basically as I'm increasing the length, the probability of transmission is decreasing. There is less transmission. As L approaches to infinity, which was the case of the step potential, as L is infinity, then what do I expect? Transmission to be 0. That's what we got in step potential. That when the L is infinite, but still there is a finite probability, because this is a ideal case, okay, which does not happen. Still there is a finite probability of tunneling. Okay, so here when there is a finite width, then what will happen? There is a tunneling, and when there is a finite, but as the height of the barrier and the width of the barrier increases, T decreases. Now I would like to think of few exercises. One, you take that your V0 goes to 2 V0 is increasing, but L goes to L by 2. Why I'm doing this? I'm keeping the area and the curve same. Then how T behaves? Fine. Now, if the length goes to 0, V0 tends to infinity, and the length, the width of the barrier tends to 0, such that V0 L remains finite. It means again, basically what it is, a delta function. Yes. So V0 tends to infinity, L tends to 0. That would be my case of my next topic of my real solids, what actually happens, what the electron experiences inside the solid. That L goes to 0 and V naught tends to infinity. The barrier is infinite, still in such a way that V naught L remains finite. That is my case of real solid. Okay, I would like to do, I would like you all to think about this as V naught increases, how T behaves. Okay, so I stop here. I hope you got the flavor, what we are approaching to. Now, these were all the toy problems. We would be approaching to more realistic problem in real solids. What do the electrons they really feel, they really experience in the presence of such kind of potential? We will be doing the application for that. Okay, thank you.